Hello everyone, and thank you for joining us to discuss our latest flood hazard data and catastrophe model for the UK. I'm Holly and I'm the marketing manager here at Fathom, and I'm joined by Dr. James Savage, who is the senior developer responsible for Fathom's global flood model, Fathom Global, and who has also led the development of our UK flood hazard data that we're presenting on today. Dr. Oliver Wing will also present on Fathom UK CAT later on in the webinar. He is Fathom's Chief Research Officer and is behind the publication of many well-known papers within the hydraulic field. Most recently, he published a paper just last week where he explores the methodology behind simulated historical flood events and on a continental scale. Just quickly before we start, we will be answering any questions at the end of the webinar. If you have any, just write them out and send them through the Q&A panel in the menu at the bottom of your screen. You may already be familiar with the work that Fathom do, but for those who aren't, we are a global flood mapping company based in Bristol. Our founders formed the company whilst completing their PhDs at the University of Bristol Hydrology Group in 2012. And we are a research-led organisation with academia and science at the forefront of everything that we do here. We are publishing papers every month at the moment and have an ambitious research agenda for 2021. So keep an eye out for lots of exciting research that we will be circulating throughout the year. And if you do want to access any of these papers that we have produced, you can do so through our website. But since 2012, the company has grown significantly, and now Fathom's data is being used by a range of organisations across multiple sectors such as insurance, international development, emergency response, and climate change. And this is both on a global and national scale. And it's our mission to become a world leader in the field of understanding climate risk. And our products and research allows us to put the data surrounding climate risk in the hands of decision makers so that they can mitigate that risk. Just to make you aware of some of our products, Fathom has a number of different flood maps and catastrophe models. Fathom Global contains data for 221 countries, and we recently updated it to version 2 just 3 months ago. It offers flood hazard data across the globe at 90-meter resolution, and like all of our products at Fathom, simulates flood risk for 10 return periods. Fathom US is one of our more widely known models and predicts flood risk for pluvial, fluvial, and coastal perils. Professor Paul Bates actually recently published a peer-reviewed paper on this, which validates all of the methodologies and science underpinning the model, and you can access that for free online if you want to. And for the US, we also have a CAT model available that can be accessed through our partners, NASDAQ, Exceedance, and Complex. But if you are interested in these products, you can find much more information through our website, which is www.fathom.global. But for now, I'd like to hand you over to my colleague, James.
Thanks, Holly, and thanks everyone for joining us today. So my name's James, and yeah, I'll be talking through our new UK hazard data. This is something we've been working on over the last year or so, and we're looking forward to sharing this with you today. So I'll start giving you a quick overview of the Fathom UK hazard data that's available before going into some more detail afterwards. So Fathom UK covers 3 perils, so fluvial, pluvial, and coastal, with UK-wide coverage at 10-meter resolution. And we use a consistent modelling methodology. So what I mean by that is we deploy the same set of core approaches to building our models throughout the UK, resulting in a spatially coherent set of hazard layers. And we model every river within the UK. And for each peril, we model 10 return periods, ranging from the 1 in 5 flood to the 1 in 1,000 year. And we provide defended and undefended models, which I'll discuss in a bit more detail later on. We also have a range of future climate change scenarios across different time horizons to allow anyone who uses data to explore risk in both the present day and into the future. So just to provide a bit more information on the types of flooding that we do model, our fluvial data represents flooding as a result of rivers overtopping their banks. Our pluvial data represents flooding as a result of heavy rainfall, such as surface water flooding in urban locations, as well as flooding within small river catchments. And our coastal model represents flooding as a result of storm surges, which increase the water level of the sea and estuaries and flood out onto the floodplain and surrounding lands. So these are the main components of the Fathom UK dataset. So I'll go into a bit more detail as to what's behind these layers. At the core of Fathom UK is a hydrodynamic model that's been continuously developed over the last 30 years. This is an efficient but accurate model, which allows us to model flood dynamics accurately over large scales, and is what really paved the way for us, our initial products, Fathom Global and Fathom US. And these model developments, alongside all our methodological approaches to modeling and model validation studies, are all published in world-leading, openly available academic journal articles. And this is really a key philosophy of us as a company. So to have research driving our approach and to be as transparent and open as we can be. And we believe this ultimately leads to a better product for users of our data and more transparency. So anyone who wants to use our data can understand it more. So on the right-hand side here is a simulation of an extreme flood event in Tewkesbury. And this is one of the thousands of simulations that underpin the UK flood hazard data. And in addition to having an accurate hydrodynamic model, there are many important data sets that underpin these simulations, such as the boundary conditions used by the models, the underlying terrain data sets adopted, and the representation of river channels. And so each of these has a crucial role to play in simulating flood events, and I'll just go through these now. So for alongside this having an efficient and accurate model, another important part of building a national scale model is to have an appropriate methodology to estimate extreme river flows within river channels. And so thankfully in the UK, there's an extremely dense network of river channels with the National River Flow Archive dataset, as you can see in the map on the right, with excellent coverage across the UK. And this means it's possible to take historical gauge data from all of these gauges and estimate extreme river discharge for any river. And we do this using a methodology based on the Flood Estimation Handbook, or FEH, which is a widely adopted methodology for estimating extreme river flows within the UK. However, arguably the most important part of building a flood model is to have an accurate terrain data set underpinning it. And this is really important for accurately simulating the flow of water on floodplains and identifying important flood flow pathways. Again, for the UK, we're in a great position for this, as there's extensive LiDAR coverage across the UK, and this provides us with a highly accurate terrain data set at fine spatial resolutions. And where LiDAR is not available, we adopt the OS Terrain Ordnance Survey terrain data sets to fill in the missing gaps. One important thing to emphasize is that LiDAR is something that's continuously being released as more and more data becomes available. And so this is an example showing kind of the area of LiDAR that's become available over the recent years. So the red data shows LiDAR available up to a couple of years ago, while the blue data is the additional data that was released up to 2020. And so this is really important because there's quite a lot of new data that's become available. And the incorporation of this new LiDAR data results in significantly more accurate estimations of flood risk. And as we move forward, we'll look to continually update our model as more and more data becomes available so that we can continue to provide what we believe to be the best representation of flood risk. So another important aspect of flood modelling is to ensure that the rivers are correctly represented within the model. So we use Ordnance Survey data to identify the locations of rivers, and the Fathom UK product also takes advantage of a new methodology that's about to be published in a leading journal, Water Resources Research, and that presents an improved approach to estimate channel bathymetry across river channels. And the most important part of this in terms of our hazard and CAT models is that the improved representation of river channel geometry has resulted in better simulations of high frequency flood events. And this is really important as these are the events that drive the annual average losses within the CAT models. So to summarize so far, we've taken advantage of the latest available data and methodologies to produce what we believe to be an excellent suite of flood hazard data. So I'll now go on to provide a bit more information on the products and show you some of the hazard data. And on screen at the moment, we can see that we're going to start with our fluvial model. And we're fortunate to be able to validate our models for a range of locations thanks to the availability of flood risk maps from companies like the Environment Agency and Natural Resources Wales. And so here are two examples as our hazard data in comparison to the Environment Agency flood maps. On the top panel, we've got Tewkesbury, and on the bottom panels, we've got Reading. On the left-hand side is the EA Flood Zone 3 map. So this corresponds to locations at risk of a 1 in 100-year flood, meaning we expect a flood to happen in these locations at least once every 100 years. And on the right are the Fathom UK fluvial flood hazard maps for the 1 in 100-year flood. And as you can see, there's good correspondence between the EA flood maps and the Fathom hazard data. But it's also worth pointing out that with the Fathom UK hazard data, you'll also be able to access the modelled water depths as well as seeing the locations that are flooded. So that'll help you gain a better understanding of flood risk for assets of interest. For our pluvial model, we incorporate the same terrain data and channel network that's in our fluvial model. But instead we take hourly and daily gridded rainfall data from CEH, the Centre of Ecology and Hydrology, to calculate extreme rainfall totals for different return period events. So this is an example on screen for Nottingham, and you can see flooding being picked up along small channels to the bottom right of the image, as well as flooding and depressions in the city centre as a result of surface water flooding. For our coastal model, we utilise an extreme sea level data set released by the Environment Agency a couple of years ago that provides estimates of extreme sea levels for different return period events at high resolution along the UK coastline. We combine this with UK tide gauge data and estimates of wave setup to simulate extreme flood events along the coast. And we also utilise the same terrain data sets that we used in our pluvial and fluvial models as well. And so this is an example on screen for North Somerset, where we have the Environment Agency Flood Zone 3 map again on the left-hand side and the Fathom coastal hazard data on the right-hand side. And again, you can see good correspondence between our data and the Environment Agency data. And this gives us confidence that our model has skill at simulating flood hazard and is appropriate for simulating both different return periods and future climate change scenarios as well. And also, I just want to add now that later in the year, we plan to publish the validation data and the full methodologies that are underpinning the UK Fathom UK hazard data sets. So keep an eye out for that later in the year. So another important part of flood modelling is the incorporation of flood defences. And this is really important, particularly to obtain realistic views of risk in urban locations. And so we've incorporated openly available flood defence data sets, such as those provided by the Environment Agency and Natural Resources Wales, which can tell us the standard of protection or the heights of the flood defences. And in addition to that, Ollie's developed an algorithm which detects flood defences or other topographic controls, flow control structures such as levees and embankments directly from high resolution LiDAR data, and then we can add that into the model. And so on the screen to just show you the benefits of this is an example for Exeter. And this is our undefended fluvial model, and you can see that there's extensive flooding throughout the city centre. If we switch to our defended model, we can see that the impacts these defences have in protecting these urban locations of flooding. So it shows it's clearly important to consider flood defences appropriately, particularly where you may have assets near to them. As mentioned at the start of the webinar, not only have we undertaken modelling to understand present day flood risk, but we've also simulated future climate change scenarios as well. And so we think this is really important as the UK climate and surrounding sea levels are expected to change significantly into the future. And we believe it's important to understand the impact that these changes would have on future flood risk. So for our fluvial and pluvial models, we've utilised the UK CP18 set of future climate projections, which have been developed by the Met Office. And we believe this provides the best and most up-to-date view of how UK climate may change in the future. We run our models for various future emissions scenarios and time horizons as shown on the table on the screen. And these emissions scenarios range from RCP 2.6, which is a low emissions future, to RCP 8.5, which is a high emissions business as usual feature. And we've also simulated flood hazard layers for worlds at a 2 and a 4 degree warming since pre-industrial era as well. So how do we incorporate these future climate change simulations within our modelling? Well, for our pluvial model, we do this by calculating changes in extreme precipitation between the present day and the future. An example of this is shown on the bottom half of the screen, which shows that for many locations, we expect rainfall intensity to increase, and for some locations, even as early as 2030. We expect the largest increases in rainfall to occur across western parts of the UK, such as Lake District and parts of Wales. And so we drive these changes through our flood models to understand what the change in flood risk is. For our fluvial model, we go one step further and we take present day and future rainfall estimates, and we run these through rainfall runoff models to estimate how river flows may change in the future as well. And then we rerun our hydrodynamic flood models with these changes to model the impact on flood hazard. For our coastal model, we take sea level rise estimates taken from a leading scientific journal article for the same emissions scenarios and time horizons, and we simulate the impact that the sea level rise would have along the coast in all of these future scenarios. And just to provide an example of these, we've got a set of images for Avonmouth representing different severities of flooding in the present day, and in 2070 for the RCP 8.5 scenario. So blue represents present day flood risk and red represents flood risk in 2070. And what we can see is that in many locations, they experience a greater risk of flooding in the future, with the most acute of these changes for higher frequency flood events. So for example, there are some locations that are currently only expected to flood once every 50 years, but in the future may be expected to flood once every 10 years. So it's therefore clear that as the impact of climate change becomes more important to quantify, particularly as a result of regulatory changes coming through, understanding the impacts of these changes on flood risk will be vital to understand And we believe that our future flood hazard data will enable users to do that. So having said all that, I'll now pass over to Ollie to discuss some of the wider UK implications of climate change, as well as introducing our new UK CAP model.
Thanks, James. Hi, everyone. I'm Ollie. So I'll just walk you through some of the work we did in quantifying risk when it comes to present day and future climate change. So using both of our present day and future projections of flood hazard, we just did a quick examination on what impact this might have on risk. So for our present day layers, we did a simple count of how many buildings in Great Britain fell within our 100-year inland floodplain. And we found just over 1 million properties have at least some flood risk at the 100-year level, or just under 3% of the UK's total building stock. You can see that there are hotspots across the country, really. This proportion rises to the teens of percent in places like Cardiff, Windsor, and Warrington that particularly stick out. So how does this change under a high emission scenario to 2050? Well, you can see that that map's got a whole lot darker. The number of at-risk buildings goes up quite dramatically in 30 years' time, I'd say. That's a 24% increase, so 1.35 million. So where do we see some of these big changes? This map shows you the increased number of properties at risk within a county or unitary authority as a proportion of its building stock. So for instance, Neath Port Talbot in South Wales sees an additional 4% of its building stock at risk by 2050. Today, there are 5 counties or unitary authorities that have more than 20,000 properties at risk of 100-year flooding. By 2050, we project an additional 7 counties will join that tally. You can see that the changes are most acute towards the west of the country, which is consistent with where James showed us intensifying extreme rainfall. The overarching summary of all this is that patterns of risk are going to change as the climate warms, and it would be wise to be abreast of those changes. I'm eager to emphasize that an understanding of today's risk and the associated uncertainties in modeling that should be your primary focus. But the point is that we're expecting that risk to be a constantly moving target across what are pretty short timescales. Climate change matters all over the country, and it will surely have a material impact on flood losses in the UK. So on to CAP modeling now. What we've been discussing up till now relates to static hazard mapping, where you simulate floods of a fixed probability everywhere simultaneously. CAP models, as I'm sure you all know, require an idea of what real flood events actually look like. And to do that, we have to model flood correlations in space. How likely are 2 locations to be in flood at the same time? So to do this, we simulate 10,000 years of plausible UK flood events using our published stochastic methods in tandem with rain and river flow data from the Centre for Ecology and Hydrology. And we use this resultant event set to sample from our underlying hazard layers. The little video on the screen here gives you an idea of some of the larger events contained within this set. You can see floods generally clustering intuitively in space, with the most extreme flooding within a given event, represented by the yellows, reds, and purples, occurring more locally, as you might expect. Currently, our inland flood catastrophe model of the present day is available via NASDAQ's risk modeling for catastrophes platform, and that's in OASIS LMF format, which we're a big advocate of as a vehicle by which we can get our scientific expertise into the hands of those who can make use of it. Other OASIS deployment options via Exceedance and Complex will also soon be available. The addition of the coastal model to this inland CAP model, as well as producing a climate change CAP model, should hopefully be released sometime in the summer. So away from some of the physical modeling now, I'm going to talk to you a bit about loss functions. I think this is a fairly understudied feature of flood risk modeling and is commonly a component subject to quite unphysical fudges in order to produce realistic losses. More charitably, we call this process calibration. But in our model, we prefer to provide an expert view on the relationship between flood hazard and a given asset's susceptibility to damage. In the UK, we're in a fortunate position that the Flood Hazard Research Centre at Middlesex University has been researching flood damage functions for decades. And they publish the data annually in the multicoloured handbook and methodological updates in the multicoloured manual. These are an excellent resource to build damage models, but have required some extensive work in-house here at Fathom to make them applicable for catastrophe modelling. For instance, multicoloured manual curves are principally developed for governmental risk assessments, which compute economic losses to depreciated values rather than financial losses to replacement values, which is what commercial organizations commonly require. But I shan't bore you with those sorts of details now. But using mostly multicolored manual data as a base, we developed over 10,000 probabilistic damage functions representing all major lines of business. Crucially, we model direct damage to the building fabric and its contents, as well as indirect damages such as alternative living expenses or business interruption. The histograms I'm going to show you over the next couple of slides represent these probabilistic functions. They have relative damage between 0 and 1 on the x-axis, and the probability that the given flood depth, in this case 1.1 to 1.2 meters, causes each relative damage on the y-axis. So you can see how a given depth produces a spread of possible damages. For this example, specifically a detached house, you can see our functions account for the differential damage response to fluvial and pluvial flooding. Fluvial floods are generally of longer duration and are more likely to be contaminated than pluvial floods, which are generally more transient and cleaner. The loss module itself is a hierarchy, meaning it can give you an answer no matter how vague or imprecise your exposure data may be. Naturally, the less information you have, the more uncertain the function is. So illustrated here is a terraced house. When you know the age of it, which is in blue, the distribution is much more confined compared to where you don't know the age in orange with a more widespread distribution. The model accounts for the number of stories an asset has. Intuitively, with these contents damage functions relating to a 1-story and 2-story office. For the 2-story office, assuming an even distribution of contents, of course, half of these are mostly out of harm's way compared to a 1-story office. You can also specify the occupancy of the floors. In orange is that same 2-story contents damage function where the ground floor is occupied. In blue, the 2-story office is only occupied on that top floor, the first floor, meaning only very deep water has the potential for impact here. One final example of many is periods of indemnity when it comes to indirect damages, such as ALE and BI. This simply illustrates that this particular flood depth in this particular non-residential property puts it out of action for more than 6 months. So you'll be covering the full amount for a 6-month period of indemnity. If your period of indemnity is 12 months, in this scenario, the business will be back on its feet before that time has elapsed, so you won't need to pay out for the full period. Here we just show how the probabilistic function sweeps through different flood depths for a very particular type of building. We've got a detached house built in 1980 with 2 stories, inundated by a fluvial flood and elevated 30 centimeters above the ground. All the various modifiers that lead to a unique damage function are listed there on the left. So more broadly, you can see the importance of representing flood vulnerability probabilistically. Commonly oversimplified and overgeneralized relationships are used where a given flood depth will always produce a fixed loss value. Hopefully this here is evidence enough that that would not be representative of the variability and uncertainty in this process. You can either bury your head in the sand or model that uncertainty explicitly. We opt for the latter. So that's the end of the meat of our technical details. I've just got a very high-level summary here of some of the key features of both the hazard maps on the left and the CAP model on the right. We're super excited at last to bring our flood modeling expertise to the nation we actually live in, coupling our efficient modeling methods to the wealth of high-quality data afforded to us in the UK has led to the creation of robust flood models to provide an alternative view of present and future flood risk. Our CAP model, we hope, makes the physical hazard simulations that we pioneer as actionable as possible by capturing their financial impact for a huge variety of buildings and both direct and indirect damages. So please do get in touch with us if you'd like to learn more, or you'd like to have a chat with one of our team, or if you'd like to take a look at any of the sample data. The link for you to do so is on the screen there.